Absolute ripper of a question here from the 2018 paper. What we've got is the y equals x sine x function. And that function there is going to be a little bit unfamiliar to us. We're just used to y equals things like sine x, and we have a constant value or a constant amplitude sitting in this spot here. Now what that produces, if it's constant, is a consistent waveform. But this one here actually has an x in this spot here. And we'll note that as x increases in the positive direction, what it will do is multiply by an increasingly large value, and it just produces or yields this interesting waveform. All right, let's see where this wants us to go. So given that the integral of x sine x equals that, can you do that integral when n is a positive even integer or 0? Okay, I can. So let's try 0 out first of all and see what happens. So what I want to do is evaluate this. So that's the antiderivative there, sine x, take away x cosine x. And let's pop 0 in for n. So that's 1, that's pi. And 0, that's 0. All right, what's it getting us to do? It is pi and 0. We're calculating the area under the curve between pi and 0. So that's what this is actually asking us to do. All right, so let's pop pi in. So sine of pi, okay, is 0. Take away pi. Cosine of pi is equal to -1. Take away 0. Sine of 0 is 0. 0 times that is going to be 0 anyway, so no need to pop that in. That's going to be pi. Okay, so it's basically got an area of pi units squared. All right, now we want to do when n is an even positive integer. So n is equal to, say, 2, 4, 6, 8, ... Okay, so sine x, take away x cosine x, and what we're going to slam in this time is n plus 1 pi and n pi. Now, this might seem a little bit weird to do this, but actually we'll know a lot about the exact values of this because n is even, so I know that for a fact. So it's going to be like 3 pi, 5 pi, 7 pi, 9 pi. It's going to be odd pi. So that's going to be always odd pi. Now, if n is even, this one here is going to be 2 pi, 4 pi, 6 pi, 8 pi. This one's going to be even, okay? And so here's odd pi and here's even pi, and I know exact values for both of those points. So I'll be able to actually evaluate a fair portion of this. So let's see how we go. We're going to slam in odd pi into sine. So odd pi goes into sine and we get 0. Take away n plus 1 pi for x. Cosine of odd pi is equal to -1. Take away. All right, even pi goes into sine and it's still 0. 2 pi goes in, or n pi goes in there, so even pi, so that's not 2, that's n. N pi. All right, now let's do our evaluation. So that's going to be n plus 1 pi take away or plus n pi. Let's pull out pi as a common factor, and we've got n plus 1 plus n, which is pi to n plus 1. All right, let's see if we can understand what that actually, that's basically the rule to get the area under the curve when the top integral is odd, like 3 pi and 2 pi. So that could get us the area there. It could get us the area there. We can test it out quickly for between pi and 0 because n will be 0 in that case. Okay, n will be 0. So 0 goes in, that's 0, 1, that's pi. And that matches up perfectly with what we evaluated first up. Okay, so that's what it's trying to get us to do and to understand. So make sure when you're doing these problems, you understand what the kind of the purpose is, what they're trying to get you to understand. That's what the key is there. All right. Now, where I presume this is going is it's going to get us to get these negative ones. So given that the integral of x sine x is this, evaluate that when n is a positive odd integer. So n this time is 1, 3, 5, 7, dot, dot, dot. All right, let's do it. Sine x, take away x cosine x, n plus 1 pi, n pi. This time n is odd, so an odd number plus 1 will always create an even number. So that's going to be even, and that's going to be odd. So we're going to get a similar result to last time, albeit the answer should be negative because the signed area below the x-axis will be negative. Okay, so let's chuck even pi in. So even is this one here. So that's going to be sine of even pi is 0. Take away n plus 1 pi. Even pi cosine is 1. Take away. Odd goes in. Odd pi is over here, which is 0. Take away n pi. And odd means that that one there for cosine is going to be negative 1. Okay, let's tidy up a bit. Negative n plus 1 pi. It's positive, take away n pi, which is negative. Let's take out pi as a common factor. N plus 1. What's that going to be? Plus n, which is negative pi 2n plus 1. All right, and that seems to be okay. Okay, so n is 1. 2 times 1 is 2. 2 plus 1 is 3. That's negative 3 pi. All right, sounds okay. So that means that this one here would be negative 3 pi. So I presume when n is 2, it's going to be 5 pi. 2 2s are 4, plus 1 is 5. That's going to be 5 pi, etc., etc. So this will be negative 7 pi, and so forth. All right. Find the equation of the tangent to y equals x sine x at the point blah, blah, blah. Okay. So I'm going to go let y equals f of x equals x sine x. U is equal to x. V is equal to sine x. Du dx is equal to 1. dv dx is equal to cosine x. So that means f dash x will be x cosine x plus sine x. All right, now why did I do that? Well, what I want is the equation of the tangent. So what I'm trying to do is fill in y take y1 equals m, x take x1. So I've found the gradient function. Now I'm going to check out what the gradient is at this point, and then I'll slam in this point into this. So let's do f dash negative 5 pi on 2, which is negative 5 pi on 2 times the cosine of negative 5 pi on 2 plus the sine of negative 5 pi on 2. Okay, that's negative 4 pi on 2, take away another pi on 2, so we're going here, we're here. So the cosine there is 0, so that chops that one out. The sine there is negative 1, so take negative 1, which is negative 1. So that's our gradient at the point. So we're going to go y take y1, now that's this, y take 5 pi on 2 equals negative 1, x take x1, which is x plus 5 pi on 2. Y equals negative x take 5 pi on 2 plus this 5 pi on 2, which they cancel out. Here is this. So it seems a little bit weird to find that, but that probably will come into play a little bit later on, we'll see. Okay, we've got a translation T maps the graph of this onto this, where A is a real constant. So we want to take this graph here, the original graph, onto some sort of new graph. And they're telling us that it's a translation. All right, so here's our original graph, x sine x, and we want to send it to this one. And I've got to do a translation. So interesting. So this is a bit different from, well, all of the mapping questions that we've seen. So yeah, let's work it out. Okay, so let's just say that I've got a function f of x equals x sine x, and I wanted to do a translation. Let's just say the translation is 2 units to the right. That's going to be x take 2 sine x take 2. So we can see here that something's been done to this function here, and it's some sort of a translation because they've dropped something into the function like this to move it. All right, and I'm going to suggest that what they might have done is I think they might have tried to shift this graph 3 pi units to the right. Okay, that's what I think has happened here. Okay, now how do I know that? Well, if I want to shift 3 pi units to the right, what I do is I go f of x take 3 pi. So that sends the graph that way. But if you want to do it via the mapping, what we can do is note that with matrices anyway, x dash is going to be x plus 3 pi. That's what I'm suggesting, is 3 pi to the right, which means that x equals x dash take 3 pi, which is what I would put in there. So let's try that transformation and see what happens. X or y equals x dash take 3 pi sine of x take 3 pi. All right, so it's sort of looking right, but not really. Okay. Now, what has happened to get this to its correct form? Well, you'll note here that they're moving a sine graph, which has a period. So it has a period of 2 pi. They're moving it 3 pi units to the right. So here's our standard sine graph, which will go to 2 pi. And what we're doing is we're picking that up and moving it to 3 pi. So it would start like that, which if you'll note, will actually be the same thing as just reflecting sine x in the x-axis. It yields exactly the same result. Try it on your calculator or GeoGebra or something like that. So if you said to me, if I said to you, listen, girls, I want you to move a graph pi on the sine function pi on 3 to the right. If one of you guys said, can I just reflect it in the x-axis? Absolutely, absolutely. So we're going to actually do that instead. We're going to say that that's x take, and I'm just going to drop those dashes there, sine x. It's exactly the same thing reflecting in the x-axis as it is moving 3 pi units to the right. All right, so the final thing is to get it looking exactly the same is we'll just go and pass that negative through or distribute it, 3 pi take x sine x. Okay, and that makes the correct function. Okay, so I know that therefore a has to be equal to 3 pi. A lot there for 1 mark, okay? And all you needed to have is a equals 3 pi. That, you don't need all of that working out, but how you see that just from looking at this, I'm not 100% sure. All right, and on to the final question of the paper. So what we've got here is the graph. This is the transform graph, okay? So that's what it looks like. So it's been moved 3 pi units to the right and reflected. Okay, and g of x is this same function, albeit it's been reflected. Okay, so we've got the translated original function. So let's have a look at the original function again. It's up here. All right, so they've translated it, which means they've moved it 3 pi units. So that part there has moved over to there, and they've also reflected it. So basically, we're just looking at this portion of the graph, or we can look at this portion of the graph just in reverse. So that part there would be this part, okay? All right, so what we want is the shaded area, I presume. What else do we know? That these are tangents at pi on 2 negative and pi on 2 positive. So it's a tangent to that one there. Now, interestingly, we also know something about these tangents. So if I go back to part B, we found the tangent at this point here, which is negative 5 pi on 2. Okay, so that is going to be negative 5 pi on 2 is negative 2.5. So what we did was found the tangent there, and we found out that it had a gradient of negative 1. All right, so that's that tangent there. So that'll be the same as that there, and like produce that triangle shape. Okay, so what I know then is that the gradient of this line here will be negative 1. The gradient of this line here will be 1. So here's my strategy. I'm going to find the full area of the triangle. So I'm just going to concentrate on only this triangle here, and then I'm just going to double my result. So A equals, what's it going to be? It is half times the base, which is 3 pi, times the height. Because it's got a gradient of 1, this has to be 3 pi or negative 3 pi to produce that gradient of 1. So it's going to be half of 3 pi times 3 pi, which is going to be 9 pi squared on 2. Okay, so that's just the area of this triangle here. So I'm not doing the whole thing, it's just this one here. Now what I'm going to do is get the area of this bit, and this bit. Now, those general formulas that we worked out in A part 1 and A part 2 are actually going to help us with this portion here. Now recall that one there is just this one here. Okay, so again, what's happened is we're just looking at this in reverse. And we know that this one here is pi. We know that this one here is negative 3 pi or 3 pi. So it's going to be pi plus 3 pi. And this one here is going to be 5 pi. All right, and that's going to be 8. That's going to be 9 pi in total. So if we go down here, what we're going to do is note that this shaded area here is going to be, so area shaded is equal to the area of the triangle subtract the area of these parts here, which I just worked out was 9 pi, and then we're going to multiply the result by 2 because it's double that. Okay, so what that's going to be is, we multiply it by 2, it's going to be 9 pi squared, take away 18 pi units squared. Right, so a pretty brutal question, that one there. Hope that helps you visualize the different parts, and it also helps you kind of understand how a question is not just made of individual parts, but one big story. So this is all a story revolving around kind of all these things are really important pieces of the puzzle when you're doing it. Okay, so none of these really are mutually exclusive of the rest of the paper, okay, or the rest of the question. This part here was relevant to understanding, you know, that these gradients were 1 and negative 1, etc., etc. So again, I'd encourage you guys to keep your paper, don't fold your paper up, but open it up and have it as an A3 spread so you can kind of get the bigger picture. I bet you this question here fell on a double page spread, okay, or a lot of it would have anyway, okay. So make sure you are, if you hit this last question here, flicking back to the first part, trying to work out why they get you to do different things is really important.